Good evening. So this is week 5 of this problem solving session. So today I will discuss some of the first. I will recap the week 5 contents and then we'll start with the problems.
Good
So
evening,
if you
sir.
have any problems, yes, hello. Good evening.
Good.
So if you have any problems from your side, then we can discuss that first.
Sir, actually, this week I do not understand the communication complexity of GRR degree reduction method.
Okay.
So I will mention that video. So uh, video is share circuit evaluation in the pre-processing model,
Yeah.
and this is video lecture number 27, and specifically, the time is 20 minutes and 55 seconds.
Okay. So I cannot watch the video right now because I'm sharing my screen and everything. So can you just
Okay.
tell me what was actually being discussed on that video?
So in pre-processing model,
Yeah.
the sir has calculated the communication complexity with one round with order of n square communication or two rounds with order of n communication.
Yeah. Yeah.
So I do not understand how that one round with order of n square communication or two rounds of with order of n
Okay.
in the case of pre-processing model.
Okay. So first of all, forget about pre-processing, but think about only this one. So suppose that we have some secret which has been secretly shared among multiple parties. Let's say n many. It's okay. So
Actually,
instead of n
actually,
many
s-
parties, yes.
actually, sir, I am finding difficulty in finding the communication complexity and round complexity.
Okay. 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 I will discuss that. But I mean, just for a simple case, so if we have a secret S, and if the secret shares are S1, S2, S3, S4, S5, and S6. So, so let's say the case is that if all of the shares are available to someone, then they can regenerate this secret S. Okay, so if that is the case, so so in that case, there are two possible cases. What we can assume is that one round of reconstruction or two round of reconstruction. So the communication complexity that you are mentioning is because of this reconstruction phase. So if we want to reconstruct this secret S, so how can this P1 to P5, oh sorry, P1 to P6, all these 6 parties can do? So if they only just want one round, meaning that uh, in just one go, they just want to share everything and they don't want to communicate anytime soon. So that is the only communication that they need to do. Okay, so that is round one. So if they want to do this reconstruction in one round, so what they can do is that P1 can send his share to each and every one of the other parties. P2 can send his share to each and every one of the other parties, like P1, P6, P5, P4, P3, and so on. So basically, each of their parties, they send each of their shares to every other parties. Now, when we say about communication complexity, so that means that how much data are being communicated in the network. So in this network, there are 6 parties, and how much data are being communicated in this network. So P1 is sending this S1. So let's say this is one group element, or rather, each of the share has size. Let's say, what can we say? Let's say
Log
this
of f.
is, yeah, okay, log of f, but let's say that is okay. We cannot use S, but okay, let's say that is X. So X is basically the log of uh, that Q, and Q is basically that group that we're considering ZQ or something like that. Okay. So X is the size of each of the shares. So now if P1 is sending this S1 to each and every one of the other parties, then how much data are being communicated by P1? So that should
N
be n
n number
minus
of
1,
n
not
minus
n
one
number,
field.
because yes. And similarly, if P2 is trying to send each of, I mean, his share to each and every one of the parties, so that will be again n minus 1 times x. So if we consider all of the parties and the amount of data that they are sharing in the network, or not sharing, but rather communicating inside the network, so that should be n times n minus 1 x, which is order of n square, right?
Okay, sir.
So when we talk about one round of complexity, sorry, one round of reconstruction, so this reconstruction phase, so this will take order of n square time uh, in order to generate this S, the secret S, from this all these shares. So if that is one round, if we want only considering one round, but there is one other process to do this reconstruction, that is when we
Sir, in
have
the
only,
previous example, in the
yeah,
previous case, uh, P1 is sharing its shares to P2.
P1 is, yeah, so usually they don't do that, but if the all the computation has been done and they want to reconstruct this secret, so there are two possible ways to reconstruct, right? So all the parties, they can share their own shares to each and every one of the parties, or they can share this. I mean, all the parties share these shares to only one designated party. He or she does the computation, and then once the reconstruction is done, he or she will distribute this secret S.
So this is the final phase of the reconstruction.
Yes, yes. So final phase is reconstruction. So initially,
And
yeah,
and the communication done in initial phase.
yes. So there are also communications in the initial phases, but I'm not talking about that. But mostly the communication, I mean, like you said in the GRR model, so the communication complexity is order n square and everything that you told me before. So that is because of this reconstruction. So there has to be some reconstruction phase done in the reconstruct. I mean, this when we are doing this in the pre-processing model, because there are this AI, sorry, A1, A2, A3 up to AN, and B1, B2, B3 up to BN, right? And C1, C2 up to CN. So these are already pre-processed, and what they do is that they communicate this, sorry, so they generate this D1 is equals to some X1 minus A1, DI is equals to XI minus AI, and EI is equals to some uh, YI minus BI,
Sir,
something like
sir,
that.
my question is also that this ABC are shared by the parties.
Yes, this ABC are this A1 is A1 and B1 and C1. These are uh, so P1 holds this share, P2 holds this share, and so on. PN.
Initially, who will share this A?
Oh, so initially, okay. So I will get to that. Let me just first finish this up. Okay. So first, so as I was saying, so there the complexity is n square, but if we do this kind of reconstruction, like you have P1, P2, P3, P4, P5, P6. So six parties again. Each and every one of them has S1, S2, S3, S4, S5, and S6. So what they can do is that they can designate one of them as their leader, or anyone, but I mean, I don't know. So they designate, let's say, P1 to reconstruct the secret. So what they will do is that each of them would send their share to P1 only. And we are only considering the honest, I mean, sorry, uh, I mean, we're not considering that the parties are malicious. We are only considering that they are honest parties. So what P1 will do is that P1 will reconstruct the secret S. So this is one round of communication, meaning that all the parties send these values and they send their shares to P1. So that is one round of communication. So after that is done, P1 would have to use this S1 to up to S6, all these values, and you would have to communicate this, generate this S. And after this S is generated, this S will be sent back to each and every one of the parties. So there are these two rounds of communication. But even though there is two rounds of communication, if the question is that how much data are being communicated in this network. So in the first round, there are n minus 1 times x. So this many data is being communicated. And again, in the second round, the same amount of data is being communicated. So this is order in communication. So the communication complexity over here is order n, but the how many round is over here. So there are two rounds. You cannot do this in one round. There in the first round, everyone has to send their data to one designated party, and that party has to generate this S from all these shares. So after the generation is done, then he or she can distribute this generated value to everyone else. Okay, so
Okay.
so this is the reconstruction phase. Now the question was in GRR model, how this A1, A2 are generated, right? So what happens is that, so if we have all these parties, P1, P2, P3, up to Pn, so they randomly generate first this A1, A2, A3, up to A. So these A1 to AN, these are randomly generated.
That
Okay.
algorithm is a robust data extraction, random extraction.
Yes, random extraction algorithm. So, so these A1 to AN, these are randomly generated. So these are completely random number from this from the group. And also this B1, B2, B3 up to Bn, these are also randomly generated. Now, if they are randomly generated and if this is also randomly generated, uh, wait, so we need to have a TN algorithm, right? If we want to have a TN algorithm.
In this case, if parties are generating A1, A2, if means some party is malicious,
No, no,
then
no. I mean, yeah, I mean, if we want to generate a TN case, I mean, this will work for n minus 1 comma n case, but not a TN case if they are all randomly generated.
N minus T.
Hmm. No. Okay, so so do you remember how this A1 to AN was generated? I mean, at least how was it told in the lectures?
Actually, I think N minus T algorithm is there, and in the lecture it has been told that means P1 generate A1, P2 generate A2, P3 generate A3, and
Okay.
after that we take a polynomial reconstruction of the polynomial, and then on that polynomial we will take separate n minus t points,
Okay.
and that t n minus t points are different from these points a1.
Yeah, but who does that? I mean, the whole point of doing this is that P1 would have the share of this A1 up to AN, such that after reconstruction it will give A, and B1 to up to Bn after reconstruction it will give B. But the point is that A and B are not known to any of the parties, should not be known to any of the parties. So that is the point. So let's say if P1 to up to PT, P1, P2 up to PT, they generate this A1, A2 up to AT, and they reconstruct the polynomial. But after the reconstruction, they will know A. That we do not want.
A and B, these triplet a b c should be secret.
Yes, yes. A, B, C, this triplet should be secret. Only then the protocol would work, the GRR protocol.
But if parties themselves generate ABC, then how can it be secret?
I mean, they are only generating the shares, not ABC itself.
So
They do not generate this.
shares can be generated by that algorithm, robust abstraction.
Yes, I mean, I have to look at that algorithm first. Wait a minute. In the pre-processing phase, I got this ABC I generated. Wait. Generate entities, measure. Still. Okay, so I have to look at the rand extract. So rand extract is not a simple random number extraction polynomial. I mean, it is much more complicated. I haven't seen that rand. I mean, I do not remember the rand extract algorithm. But the point is that whatever the algorithm is, it should be like this, like P1, P2 up to Pn. They are generate. I mean, at the end of the day, they should be having this A1 to up to An, such that this A is unknown to them. Okay, they should not have any idea what this A is. I mean, after reconstruction, what this A is, and this A has to be random number. Okay. So I mean, that is the only way that the pre-processing would work. So P1 to Pns, they would generate this A1 to An such that this A is a random number, and they do not have any idea about what this A value is. And similarly, they use this rand extract formula to generate a polynomial, to generate the shares of B such that B is unknown to them. Both A and B
This
are,
this random extraction algorithm is run by the protocol.
yes, by all these parties. In the protocol, whatever the parties are, P1 to up to Pn, all of them. So after that is done, so then they can apply the GRR protocol over here in order to generate the shares C1 to up to Cn, so that this C is basically nothing but the multiplication of A and B. So that's how they generate this A, B, and C. So they only use the GRR protocol over here. And in order to do that, they need a communication complexity of order n square over here.
Sir, why order n square?
Because in the GRR protocol, okay, in the GRR protocol, if we have the shares A1 to up to An for A and B1 to up to Bn for B, then what we do is that first we just component wise multiply these two shares, and we first have this S1, S2 up to Sn, which is nothing but the multiplication of A1, B1, A2, B2, and A and B. So now what we do is that, so if party 1, the P1 has the share S1, P2 has the share S2, and Pn has the share Sn. So P1 now shares this, I mean, generates the using a summary secret sharing protocol, it generates the n many shares for S1. So like S11, S12, S13, and so on. S1n, S21, S22, S23, S2n, and so on. So these are all generated and shared among all the parties. So how many shares are generated? And once the shares are generated, so all the shares are supposed to be sent to other parties, right? So
So
that value,
S1 is the product of AB.
S1 is the product of A1 and B1.
A1 and B1. Okay.
Yeah. So so once these are shared among all the other parties, so I mean these values have to be shared among all the other parties. So P1 like share I mean sends these values to other parties. P2 sends these value to other parties. And all the diagonal elements, only the diagonal elements, they are not to be shared because I mean they generate them. I mean P1 generates this S11 and keeps it to himself. P2 generates this S22 and keeps it to himself, and so on. So what is the number of elements that are shared in the network? So that is total n square minus n many elements. So that is nothing but order n square element. So that's why the communication complexity in this case is order n square.
And
So
the communication which has been done for sharing A and B
yeah,
in the previous
communication
in the previous example.
in the previous one, this one,
No, no. We have recently, which we are doing recently.
this one,
S one. S case.
S.
Yeah, yeah. This one. This table.
Okay, in this one,
Sir, no. This one not. We are you just we are solving this one.
okay, this one.
So in this one, this is the final step communication complexity is order of n square. And
Order n
what is the
square. Yeah,
communication complexity of sharing A and B's with the party?
this one.
Yes,
So
A's and
this
B.
uses this rand extract function. I mean that I have to look into. I mean, what is this rand extraction is actually doing? So I don't remember this rand extract function very well. So I have to look into that. Okay, but I think that is also order n square because I mean the whole GRR protocol it takes order n square. So it has to be something. I mean it can be either order n square or order n, but it has to be less than order n square, not more
And
than that.
if it is order of n square, the
Yeah.
overall complexity will be order of n square.
Overall complexity is also yes order n square. Yeah.
Yes.
Because I mean there are only a finite number of steps, uh, only 3 steps. So first you have to share this all the values of a. I mean you have to share this shares of a, this value a. Then you have to share the shares of b. So that is 2 steps. And after that you can generate this S1 without any communication. This S1
And
to up
sir,
to
if
Sn
we do the S1 by using the two
by using 2
rounds,
rounds. Okay.
and then can we have the communication complexity order of n?
So the over here we do not have any reconstruction phase anyway. So the 2 round or 1 round case will only arrive when we have to reconstruct something. So over here we do not have any reconstruction yet. So the reconstruction happens when we have this A1 to up to AN, B1 to BN, and we also have C1 to CN. All of these are there, such that this after reconstruction, if we get A, B, and C, then this will hold this relation. Okay. So we first of all we have this. We do not reconstruct this A, B, or C. We do not do that. But rather, so suppose that we have x, the shares of x and y in this way, that x1 up to xn and y1 up to yn, and we want to generate a z such that z is equals to xy. We have these x and y as input, and we want to find out this z is equals to xy, and the shares of this z. That is what we want to find out. Now, in order to do that, what we do is that we first do this xi minus ai. We consider this as di, and then ei is equals to yi minus vn. So that is the first step that we do, right? And then we reconstruct this values of d, reconstruct the value of d and e. That is what we do. And as we can see, if A is not, I mean, after the reconstruction, what we will get is X minus A and Y minus B. And this is why A and B has to be random. I mean, not only random, but they has to be secret. If A and B is known to any of the parties or any collection of parties, then they can easily reconstruct X and Y from them, from that. So we do not want that. Okay, so this is what is reconstructed. So at this step, the reconstruction is needed. And at this stage, now we can argue that if there is only one round, if we use only one round of reconstruction, then the complexity, I mean, the communication complexity is order n square. Or if we use the two round of reconstruction, then the communication complexity would be order n. Okay.
Okay, sir. And the communication complexity of sharing DI and EIs are D and E are.
Sharing D and E. Also, we do not need any communication because the shares of X1 to Xn, that is with with all the parties. So the parties already have the shares of X, the shares of Y, and the shares of A and B.
Okay,
Right.
okay.
So if they already have that, they can just do this calculation by themselves.
But the final, I think, linear multiplication is needed with D and E values.
Yes.
In
So
yes,
basically, so this multiplication of X and Y, we can just write it as this. Multiplication of X and Y would be, okay. So basically, we have D plus A as X and E plus B as Y. So this XY can be written as DE plus DB plus AE plus AB. Yeah.
yes, sir. So DE, how we can get DE? We have to reconstruct the D from the shares.
Wait a minute. Is this calculation correct? Okay, so this AB is nothing but CIs, which we already have. Uh, so now, once we calculate these DIs, right, XI minus AIs, so from there we can do the reconstruction algorithm. I mean, we can use the reconstruction algorithm and we can get this D values. Okay, so D will already be known to all the parties. Even E will already be known to all the parties. So once D and E are known, the only unknowns would be this B. So this is one unknown, B, and A is one unknown. AB is also unknown, but this can be written as C. So now you can see that we already have the shares for A, shares for B, and the shares for C. And DE, DE, so all of these values, these are known to us. So therefore, this multiplication of X and Y is nothing but a linear combination of A, B, and C. And since all of their shares are available with us, so we can just you know we can just apply this linear combination on that particular shares. I mean, individual parties would apply this linear combination over there, meaning that they would apply this D BI plus AIE plus CI. So each of the shares ZI would be of this form. And they can use these ZIs to reconstruct the Z, which is nothing but the X times Y.
Okay.
So the only reconstruction that we need over here is this. And during this reconstruction, we need the communications. I mean, we need to, each party has to communicate with the other parties. And over there, the communication complexity would be either order n or order n square, depending on what kind of reconstruction algorithm that we're using, whether it's a one round or two round. Yeah, so basically in the last week, we have seen that. So we have seen what is the degree reduction problem was, and we have seen two degree reduction problems. One is based on the BGW protocol, and the second one is the GRR protocol, which is the advanced version. And this, we have also seen the analysis of GRR protocol, meaning that we have seen that the privacy condition is there or in the GRR protocol, degree reduction protocol or not, this GRR protocol. And then we have seen that how this GRR protocol can be used for shared circuit evaluation. We have seen the pre-processing model for GRR protocol. And finally, we have seen the optimality of corruption bound, meaning that the corruption bound that we always need an honest majority setting, meaning that the T or the number of correct party, it has to be less than n over 2 to be that in that way. So we cannot have T greater or equals to n over 2. We cannot have that. If T is greater than or equals to n over 2, then we cannot have a perfectly secure MPC protocol. Then, I mean, in those cases, we actually have to depend on cryptographic primitives. In those cases, in the cryptographic primitives, we will actually have computationally secure, meaning that we can say that if the MPC protocol is not perfectly secure, but it is computationally secure, meaning that if there is a polynomial time adversary, then those adversaries cannot really break this kind of security. I mean, security of the cryptographic primitives over there. So oblivious transfers are examples in those cases. But if we want perfectly secure MPC protocol, then T always has to be n over 2. I mean, sorry, T always has to be less than n over 2. Okay. So now first we will solve the last week problems. So first we have consider the n set of parties. We have P1 to up to Pn, and out of which T are corrupt. And A and B are NT secret shares through some secret sharing scheme, such that AI and BI shares held by party PI. Suppose that all the parties want to compute the product C is equals to A times B, and for this they multiply their respective shares of A and B to obtain the share C as this. Okay. And which one of this correct? Which one of them is the correct options? Okay. So first option A says that for T less than n over 2, the shares of C from the valid summation from a valid summary sharing such that the interpolating by T plus 1 shares will give us A cross B. So this is definitely not true, because first of all, this is not a valid secret sharing because it doesn't hold the privacy property. And if we also know that if A is of NT shares, like if we have A shares has been generated as this A1, A2 up to AN, and B shares has also been generated like this B1, B2 up to Bn, then multiplying them together, just doing the multiplication. So this gives us C1 to up to Cn, but this would be a n, 2t share instead of nt share. So this will not be a valid summary secret sharing scheme, but also the t value, I mean the value of t, this will be doubled. I mean, if the threshold was t over here for the initial cases, then over here the t will be doubled.
2t plus 1 shares will be needed.
Yeah, 2t plus 1 shares would be needed, but the answer says that t plus 1 would be enough, but that is not true. So option A is not true. Okay, so I think there is a misalignment. So this is option A. So that is definitely not true. Option B is over here. Okay, so for t less than n over 2, the interpolating any t plus 1 share will not give A cross B, sorry, A times B as a constant term. So this is true. So t plus 1 many shares will not give S. Okay, so now for t greater than equals to n over 2, the protocol guarantees privacy. This is definitely not true. And finally, because the protocol doesn't give privacy, guarantees privacy in any case. And even for t less than n over 2, the protocol does not guarantee the privacy. So this is also not true. So B is the only correct option. Okay. So now in problem 2, we have 3 parties, P1, P2, and P3, and each of their inputs are A, B, and C. And those A, B, C are inputs from Z5. And who want to compute this A plus B plus C without revealing any information about their respective inputs. They do not, so they do use their BGW protocol for linear functions. Fill in the following table and choose the correct option regarding the values of X, Y, and Z. Okay, so the input over here are A, B, and C. So P1 has A, B, and C. And their sharing polynomial is this. So if the sharing polynomial is this, so these are nothing but A, B, and C. So A is 4, B is 1, and C is 2. Okay, alpha is basically the point on which this sharing polynomial is evaluated. So now we have to find this X, Y, and Z, and whatever this share of A plus B plus C is. Okay, so that is what we have to find. So first of all, let us consider this one. So if this is the sharing polynomial for P1, so 4 plus 3W is the sharing polynomial. Okay, so let me just write it next page. Oh. Okay, so 4 plus, so P1, P2, P3, and P4. So they have the sharing polynomial 4 plus 3W, 1 plus W, oh, and 2 plus 6W. So there are 3 parties. Yeah. So, and their evaluation points are basically 1, 2, and 3. These are the evaluation points. So now P1 would share, P1 would generate the shares at the point 1, 2, and 3. So that would be at point 1, it should be 4 plus 3, 7. So in Z5, that should be 2. And at point 2, at 2, it will be 6.
0.
Yeah, so that should be 0.
0.
Is it 0? Because at 2,
10.
it's 6. Yeah, 0. And for 3, it should be 3, 3, 9. And for 4, yeah, 3, 3, 9, 4, 13. So it should be 3. Right? Yeah. Okay. So now similarly over here at 1, it should be 2. At 2, it should be 3. At 3, it should be 4. Or this at 1, it should be 8. 8 mod 5 should be 3. At 2, it should be 12, 14. So at mod 5, it should be 4. And it's 18, 20. So it should be 0. So these are the values that are shared with P1, P2, and P3. So P1 gets all these values, P2 gets all these values, and P3 gets all these values. So over here, the shares, okay, and also this is the shares of A, right? So these are the shares of A, shares of B, and shares of C. Over here, what we, so this is the shares of A. So shares of A are nothing but 2, 0, and 3. So 2, 0, and 3. And over here, it should be 2, 3, 4. So 2, 3, and 4. And finally, we have 3, 4, 0. 3, 4, and 0. So these are the shares. So that means the X, Y, and Z value. So this and this are respectively 2, 0, and 0. So those values have we have found out those values. Now we have to find out what is the shares for A, B, C, R. Basically, we have to reconstruct this polynomial corresponding to this shares A, B, C, A plus B plus C. So first of all, in order to find out this a plus b plus share of a plus b plus c at P1, at the party P1, so we have to add up all the shares. So since this is a linear function, we can just add up all the values. So over here we will have 4, 7, so 2. This is also 2, and this is also 2. So the shares for P1, P2, and P3 is 2, corresponding to a plus b plus c. Now the question is, what would happen if we reconstruct a 2 plus 2, sorry, these 3 points into a 1-degree polynomial. So basically we consider that the reconstructed polynomial is basically nothing but this. P of w is equals to, okay, mx plus n. We have to find out what is m and n are. Okay, mw or x. So if we consider this as the polynomial, so according to this, is that m evaluated, this polynomial
Sir,
evaluated
it
at,
may be the 2-degree polynomial.
no, it should not be a 2-degree polynomial, because see, if it is a BGW protocol, meaning that whatever the input polynomials were, so if the input polynomial is an NT share, then the output should also be the NT. I mean NT share, right? So basically the point is that, so if these are the NT shares, so meaning that they are so in order to generate these shares, they have used this polynomial, 1-degree polynomial. So in that case, for the inputs, the value of t was 1, right? Now if we are generating this output, so this output should also have, I mean the output shares, the outputs would also have t is equals to 1. Okay, so the threshold does not change, so the threshold is same for the inputs and the output shares. So over here, even though
It
there
is
are 3,
given that t is equal to 1.
yes, t is already 1, so it is given, and the share polynomials is also have degree 1, each of them. So we
Maybe
have to
they
assume
have, maybe they have 2-degree have 0 value.
2-degree.
Means
Oh, I mean, you mean that the coefficient of W square is 0?
yes, maybe that may be the case.
Yeah, but in that case, I mean, if we say that if we can consider that this is a 2-degree polynomial like this, I mean, sorry, W square in W plus something like k. But in that case, you are assuming that this m may not have a non-zero coefficient. But if we are certain that this m has 0 coefficient, then there is no longer, we do not need that coefficient anymore. We can only assume that this is nw plus k. This n may be 0. We do not know whether this is 0 or not.
Okay.
And that is also true, that we can just assume that this is 0. I mean, if we can already be certain about the coefficient of W square to be 0, then what's the point of having that in the equation?
I have applied Lagrange interpolation in this case.
Yeah, I mean, you can apply Lagrange interpolation, but there is only 3 parties, and the polynomial we're considering is 1-degree polynomial. So there is no point
And
of,
when I applied the Lagrange coefficient, automatically degree 2 coefficient becomes 0.
yeah. Yeah, but that doesn't mean that it will be the case for every other polynomials. I mean, actually it would, because, yeah, actually it would, because even if you consider all these 3 parties, and the line is something like this, right? So there is only a unique polynomial going through all these 3 lines, and
Okay.
that should be a straight line. No, but if we consider 2-degree polynomial, it can also be something like this. No, 2-degree for 2-degree polynomials, yes, okay. Okay, I mean, okay, so in this case, the case was easy. But
Now,
if for some,
if there are 3 points if you are sharing and there are 3 points,
Yeah,
and for 3 points,
yeah. I mean, this case was good, but let's say if there are four parties, if there was another party, and for that case you had a share, so something like this. So your polynomial is a straight line. Okay, your polynomial is a straight line, and there are four parties. So you have assumed t is equals to 1, since your polynomial is a straight line, and there are four parties, p1, p2, p3, and p4. And these are their shares. They all four come together and they want to reconstruct a polynomial that goes through all these through 4 points. Now, can you guarantee that there will be one? Can you guarantee that there will be a unique polynomial going through these 4 points? Only a degree 1 polynomial. It can be a polynomial something like this.
so its degree will be 1,
I think
2,
its degree is in this case the degree of the polynomial is 4. Yeah,
4.
it should be 4.
Yes.
So I mean, I don't know whether these cases may arise or not, but the best possible, I mean, the best way to do is that if we already know what the value of t is, so we just take only t plus 1 many parties, and then we just start reconstructing.
But in that case, in that question, we have not given t.
We have not been given t without revealing the information. Yeah, we have not been given t. It's true. Wait a minute. No, I think okay. So if there are four parties, we need 3-degree polynomial, right? Maximum degree can be 3, it cannot be 4.
Yes, for 4 degree, it will be 5 points we will be needing.
Yeah. So there we cannot have a 3-degree polynomial that passes through all these 4 points. We need to have a straight line. Even there is no 2-degree polynomial. So I think, yeah, I think I mean what you're doing, that would work. I mean, even if there are n many parties and if we interpolate all these n points together, so that will also give us the same polynomial. I mean, only this polynomial that is used for this secret. Uh, sorry, only the polynomial that was used to generate the secret. So we do not need to interpolate only 2 points, but rather we can just interpolate all 3 points or 4 points or all n points.
And this your methods of slope will also work.
Yeah, I mean, we need at least t plus 1 many points, right, to generate the secret. But that doesn't mean that we cannot use t plus 2 many points or n many points. We need at least t plus 1 many points.
So how you come to conclusion that t is 1 in this case? Oh, t is
Oh, I was saying t was 1 because of this degree of this polynomials that was used for generating the sharing polynomials. I
so
mean,
t
the
plus
shares.
1, t plus 1 points will be 2. So 2 points
Yes,
will be needed.
yes.
Okay. Okay, sir.
Okay, so as I was saying, so if we consider this as the polynomial, so then p1 and p2, so those are given as 2 in this case. 2. So we just put the values. So pm plus n, that should be 2, and 2m plus n, that should also be 2. And from there, we can easily say that m is equals to 0 and n is equals to 2. So this will be the solution. And therefore, in this case, pw would actually be is equals to 0w plus 2. So as you can see that even the coefficient for this linear term W, so that is also 0.
Yes, sir.
Yeah. So here the polynomial is nothing but a constant polynomial, which is 2. Yeah, so the option is this, option D.
The option.
Okay. So, I mean, problem 3, we have assumed that there are 5 parties, P1 up to P5, and they want to compute a function of their input using the BGW protocol. However, suppose that each party can have multiple shares. Specifically, the following table shows the number of shares for each party receives. So this is the P1, it has 1 share, P2 has 2 shares, and so on. With the minimum degree of polynomial required for summary secret sharing is T is equals to 2. Any 2 parties can be connected. Okay. And what is the largest value of T that for which the degree 3 polynomial is enough for summary secret sharing? So this was the kind of question that was discussed previously. So
Yes,
we
sir.
have
You have
5
given the
parties.
hint
Yeah.
of it in the previously.
Okay. So P1 has 1 share, P2 has 2 shares, P3 has 3, P4 has 2 shares, and P5 has 1 share. So as I said before, so basically we just create a virtual parties. So P1 would consider has only 1 share, so we do not need for that. P2 has 2 shares, so we will consider P2 to be different parties, and each party have 1 shares. Let's say this has share S1, this has share S1, S2, S3. This has share S4, 5, and S6, S7, S8, and S9. So total 9 shares will be there. So now the question is that what is the minimum degree of polynomial required for summary secret sharing for T is equals to 2? Meaning that in the original protocol, the T is 2. So any 2 party can be corrupted. So in order to find out what should be the minimum degree for summary secret sharing, we have to figure out how many, if we corrupt any 2 parties in this protocol, then how many parties in the in the virtual protocol that we are considering over here. So how many parties at max will be corrupted? So as we can see, if we corrupt P2, P3, so it will corrupt all these 5 parties.
5 parties.
Yeah. So at max, that is the maximum value. Even if we corrupt this P3 and P4, that will be the maximum number of parties that is corrupted is 5. So 5 should be the number in the summary secret sharing protocol. I mean, whatever the degree of the polynomial that we choose, we must ensure that if 5 parties come together, should not generate the secret. And in order to make sure that the 5 parties should not be generating the secret, so that means that we have to ensure that T is equals to 5 in the summary secret sharing protocol.
Because for that we need 6 points.
6 points at least in order to generate the secret. Yeah. Okay. And the second question is that what is the largest value of T for which a 3-degree polynomial is enough? So now it says that we can afford to have a 3-degree polynomial for summary secret sharing scheme, meaning that if there are 3 parties comes together, they cannot generate the secret, but anything more than 3, they will be able to generate the secret. So now the question is that what should be the what should be the value of T in the original protocol, meaning that how many parties from P1, P2, P3, P4, P5, so how many parties there should be allowed to generate, I mean, how many parties can be allowed to not to generate the secret. Yeah, so in that case, so it says that the maximum degree of the polynomial is 3, and as we can see, if we only have these 3, I mean, this is the maximum number of shares that holds that P3 holds. So this is 3 already. So if we use the degree 3 polynomial, degree 3 polynomial that is being used for us. So then P3 along with any party, they can generate the secret. So T is definitely less than 2. Why? Because as we can see, if P3 comes with anyone, let's say P1, P2, P3, P5, P4, so they should be able to generate the secret if the degree of the polynomial is 3. So we cannot be using T is equal to 3, but T has to be less than 3. So now the question is T is equal to 1 or not? I mean, T has to be 1. If T is equals to 0 means that no one can generate the secret, right? What it means that T is equals to 0.
P equal
No,
to 0
actually T is
means
equals to
no
0 cannot be possible.
malicious.
Yes. T is equals to 0 means that if one party comes, they can generate the secret. So everyone has the secret. So T has to be at least 1. T is at least 1, but it is less than 2. So that means that T has to be equal to 1. So in this case, option D is correct, meaning that we need the degree of the polynomial of the summation secret sharing scheme 5 if we want T is equals to 2. And if T is 3, then the largest, sorry, if the degree of the polynomial is 3, then the largest value of T that we can afford is 1. Okay. Okay, so now in problem 4, we have, suppose that there are 4 parties and they want to compute a linear function of their inputs as this. So f of x1, x2, x3, x4 is equals to this. Which of the following ways computes the function will give optimal round complexity when PGW protocol is used? So when we are talking about round complexity, meaning that it doesn't care about the if individual parties are doing the computations. So if there are 3 parties and they have some shares, let's say x1, x2, x3, y1, y2, y3, something like that. So if they have their own shares and they are doing their computation on their own system. Okay, so whatever this function might be, so let's say that f of x1, y1. Okay, so whatever the computation they are doing their in their own individual system. So they do not need a communication from other parties. That, like, let's say they are sending C1 or C2 to other parties, something like that. So they do not need any communication from other parties. So that means that in the network they do not need to send to other parties any data to other parties through the network. So then we say that there is no communication complexity. But if they send, let's say, all the parties in total, they are sharing n many data through the network, then we will say that the communication complexity is n. That means n many data is being shared among all the parties. In total, there are n many data are being shared among all the parties via the network. So now the question is, if this is the function that we have to compute, and each of these x1, x2, x3, and x4 have been are shared among all the parties. And the shares of x1, x2, x3, and x4, these are shared among all the parties. Then what should be the communication complexity?
Sir,
Okay,
I think
wait a minute.
D will be the option. All of them same round of city.
Yes, D will be the actual option, but of their inputs as this. Okay. So basically the thing is that P1 has x1, P2 has x2, P3 has x3, P4 has x4. So now what P1 does is that P1 generates this shares of x1 and shares this among all these parties, P1, P2, P3, and P4. And similarly, P2 and P3, P4, they all do the same. So that will be the only communication to communicate the shares. And once that is done, then we have the computation phase. So in the computation phase, we have to compute this this value of f of x1, x2, x3, and x4. Now, as you can see that we can write down the circuit diagram for this one. So we have x1 that is multiplied with 2 x2 that is multiplied with 3, and okay, sorry, x2 is multiplied with 3, then x3 is multiplied with nothing, and we have x4 that is multiplied with 4. Okay, x3 and x4 is multiplied with 4. So after that is done, these two are added together. So this is addition. Then x3 is added with it. Then x4 is added with it. And that is our final value. So in any way, you write down the circuit diagram for this these functions in any in any form, then you will see that all of these are nothing but linear operations. And for linear operations, we do not need any kind of communication. So first we will communicate all the shares, but after the shares are communicated to all the parties, what happens is that we do only each of the parties do individual computation on their own system for any of these cases. The total communication complexity would be the same, meaning that they will not need any communication for these computations. So that's why option D is correct. And also the round complexity is also the same, because only in the first round they need to communicate this shares for x1, x2, x3, and x4. That's the only thing that they need. Only one round of communication. And also after the shares for this, if x1, x2, x3, and x4, these are generated, so they has to be reconstruct. Okay, they has to do a reconstruction in order to generate this f x1, x2, x3, and x4. So if we consider it as this as z. Okay, so now in problem 5, we have a BGW protocol which is slightly modified.
Sir, actually, this question is my wrong.
Okay. And which option did you choose?
I choose in previous slide. I choose, I think, B and C. B and C.
B and C. S1, S2, S4, and S2, S3, S4. This one.
Yes, yes.
Okay. So over here, it says that there are n parties, and out of which t are corrupt. Suppose that party pi wants to share an m cross n input matrix mi. To do this, it will generate an nt semi-secret sharing, which is the element present in the row R and column M. These shares are then generated parallelly, and hence every party Pj will obtain the matrix this. Communication complexity is m square times that of the BGW protocol. The round complexity is the same as the BGW protocol. The communication complexity is same as the BGW protocol. Okay. And S4 says the optimal resilience required for semi-secret is determinant of the matrix is currently without any interaction is t is less than this. Okay. And the same thing with t less than 2 to the m. Okay. So first of all, we have each parties P1, P2, P3. They have a matrix. And the size of the matrix is m cross m. So there are total m square many elements in each of these matrices. So P1 generates the shares for each of these matrices and sends it to the P2. Sends it to other parties. So there are P1, P2 up to Pn. So n many parties, therefore n many matrices. So first of all, what is the communication complexity? So over here, okay, wait a minute. The communication complexity is times the BGW protocol. So in this case, what is okay? So first of all, let us consider in this case, what is the communication complexity? So each of these elements, so let's say that P1 has one element. So there are total m square many elements. So if we take any one element, and that one element has to be generated. So we generate the shares corresponding to that one element and share it with all the parties P2 to up to Pn. Right. So there are total n minus 1 many shares that are generated. Sorry, n minus 1 many shares that are communicated to all the parties. Right. So P1 shares n minus 1 many shares corresponding to one element. And since there are total m square many element, so m square times n minus 1 many shares has to be sent by P1 to each and every one of the parties. And there are total n many parties. So the total amount of shares that are communicated inside this network, that should be n times m square into n minus 1. So it is n square minus n times m square. So this is order m square n square. Right. Now it says that what about the BGW protocol? If there was only a so if we only use the BGW protocol, what would happen? So now this is basically the BGW protocol, but it is modifying in the sense that in BGW protocol, we have only considered that there is one single share corresponding to each party. Now this is slightly modified version, meaning that each party, instead of having one single share, it has a total matrix, matrix with m square many inputs. So if we only consider the BGW protocol in our case, meaning that P1 to up to Pn. Oh, sorry, we cannot consider P1 to Pn, but rather in the BGW protocol, so each matrix would have n square many element, right? So m square many element in each of the matrix. So each of the inputs of the matrix would be corresponding to each of the each parties. So we have to consider there m square time n many parties. Is that clear?
M square dot n many parties. So
Meaning that
we are sharing the matrix using BGW protocol.
yes, so basically in this case we are considering P1 to be so it says that the BGW protocol it is slightly modified, but this is nothing but the BGW protocol itself with multiple inputs. Right. I mean the description of this problem is nothing but the BGW protocol with multiple inputs. So over here P1 has m square many inputs because each matrix has m square many elements. Right. So P1 has m square many elements, P2 have m square many elements, P3 has m square many elements. Now, if we want to convert it into a standard BGW protocol, I mean the standard description of BGW protocol, then each party should be holding one single share instead of this m square many shares. Right.
Okay, sir.
So basically the case is that corresponding to each of the parties, we have to consider m square many parties. Instead of considering it as one party, we have to consider it m square many parties. And then we have to do the whole communication. So corresponding to P1, there will be m square many parties. Corresponding to P2, there will be m square many parties, and so on. So the total number of parties then becomes n m square. And now if they want to start communicating among themselves, I mean communicate the shares among themselves, so that should be n m square times, no, not n m square times this, rather that would be n m square, okay, not n m square, sorry. That should also be, yeah, so these have n square many parties, this has m square many parties, P2 up to Pn, they should also have m square many parties. Yeah, but when we are doing the communication, so communication among these m square many parties, this should be 0. I mean, basically, this is considered as corresponding to only one party, right? P1, or this is corresponding to only one party, P2, and all these parties, m square many parties, this correspond to only one party, Pn. So therefore, any communication among them is basically has zero cost, because we are not sending it via the network. The only communication that matters is the communication through from P1 to P2, P2 to PN, P2 to P3, and PI to PJ, basically, where I and J are not equal. So each of these M square many elements, these has to be shared with P2 to up to Pn and so on. And that basically gives us the similar kind of construction that we have in this modified version, that as it says. And the number of communications among all the parties would actually be the same, order of M square N square. So option 3 over here, sorry, not option 3, but S3 is actually true. That is, the communication complexity in this protocol is as same as BGW protocol would have.
Sir, why? The communication complexity is M square N.
Yes, M square N, M square N square
M
for
square
this
N
case.
square.
Yes, for this case. But if we even consider a BGW protocol, where each party, corresponding to each party, we just consider M square many parties and everything. Even in that case, the communication would be same as this one, because so as I said, so if we consider one element over here among this M square many elements, so that one element has to be shared. I mean, we generate the shares, and how many shares do we generate? We generate total M square N many shares.
And that has to be communicated to P2 up to Pn.
That has to communicate to P2, yes, P2 to Pn, all of them. So one share is generated. Wait, one share is generated. Yes, that is M square minus, so M square times N many parties. So then this many shares are generated, and all those shares has to be just shared with P2 to up to Pn.
Actually, sir, what I understand, when
Yeah,
P1 when P1 is sharing the shares of its first element, at
yeah,
the same time, the P1 is also sharing the shares of the second element also.
yeah, yeah. They are all happening in parallel.
Yes, that's why I think uh, the communication complexity can be from that M square.
Mm, three shares. Mm, okay. So this is M square N many parties. One share is over there. So M square N many parties. Share among M square N many parties. Was M square. That gives us M square times 1 minus 1 many parties. That corresponds to 1 element. Oh, no, this should not be there. No, actually, hmm, the communication complexity is M square times that of the BGW protocol. I mean, if we consider a standard BGW protocol, so that would also give us a similar kind of construction. It is not anything different. Is there any problem? I mean, is there any difference between the modified this BGW protocol against the standard BGW protocol?
Only differences of metrics.
Yes. Only difference is that there is a
And if
matrix.
we consider the BGDW protocol, which have only one element, and we
Yeah.
compare this from this matrix, then what will be the difference of communication complexity?
Yeah.
So I think P1 is treating this whole matrix as a single element, and parallelly it will shares the shares of all the elements.
I mean, if we do that, I mean, P1 is treating this whole matrix as one single element, right? So this has the size of, so what is the size of this element? So let's say this is M1, right? So M1 has the size M square times X. So X is the size of each single element. So in this case, this was the communication complexity. But if we consider this M1 who has the size this M square times X, then the communication complexity over here should be the N square times each of the elements, size of each of the elements, right? And over here, the size of element is M square X. So this should be again M square times M square times X, which is again order M square N square. And that description follows through, but the problem is that that description is exactly similar to this one, right? Because when we are saying that each of these elements are being shared using the summary secret sharing scheme, like over here, so it is nothing but the shares for this message M. So this Mij, this is considered as one share of the I mean, these are the shares for the matrix M, Mi. So it is basically what you are saying, that each of the matrix is considered as one single element. So that is exactly what it is doing in this modified BGW protocol.
And the answer is, I think, S2, S3, and S4.
The answer is given as S2. The round complexity would be same because I mean the number of round does not change, even if we modify that, because if there are n many multiplications that we need to do, then for each of the multiplication there has to be one round of communication. So so that would not be changing. The round complexity would be same, but the communication complexity would be same for BGW protocol. Why is it same? I mean, why the BGW? I mean, what does it mean by the standard BGW protocol, or what does it mean by the modified BGW protocol? So that difference has to be cleared. I don't know.
And that optical resilience to find the summit secret.
Yeah, optimal resilience, we can easily calculate that because as you can see, so it says that without any interaction, one should be able to generate, right? The summary secret sharing scheme to determine the shared matrix correctly. Okay, so determinant of the shared matrix correctly. So once we, so how do we calculate a determinant of a matrix? So if we have a matrix, let's say M cross M matrix, sorry, N cross N matrix. So if we have an N cross N matrix, how the determinant is calculated? So determinant is sum of some term. Okay, so there are multiple terms that has to be added together, and each of these terms, these are nothing but multiplication of. So each of this term I is nothing but multiplication of n minus 1 many matrix elements, right? So if we can consider this this A1, A2, just 2 by 2 matrix, A3, A4. So the determinant is nothing but A1, A4 minus A3, A2. So this is one term with just two multiplication of two elements, and this is also one term with multiplication of two elements. Okay, sorry, this should be n many elements. Multiplication of n many matrix elements. If there are there is an n cross n matrix. So each of this term should be multiplication of n cross n, multiplication of n many matrix elements. Like for 2 by 2, this is the example, and this is even though there is a subtraction, we can consider it as sum of sum like this plus minus A3 times A2. Okay. So this is just one example, but any determinant can be of any matrix, determinant of any matrix M, this can be written like this. So if a matrix can be written like that, so now the question is, so each of the matrix element is shared using NT shares, NT summation sharing scheme. Now n many multiplication has to be there. So suppose that A1 and A2 are multiplied together. Two elements are being multiplied. So if we just use the individual multiplication, not using the GRR multiplication and everything, if we just individually multiply those two shares, okay. So what would happen? So what would happen is
We
that,
get 2t degree.
yes, so that would be n 2t degree share, and this share is again multiplied with a different share A3. So that will give us n 3t, right? So
Yes.
A1, A2, A3. Similarly, if we multiply it with A4, a different share, which has, okay, so each of these are NT, right? Each of these are NT shares. So after multiplication, this will give us N4T share and so on. So meaning that if we multiply these four elements together, so that gives us N4T share. If we multiply three elements together, this will give us a N3T share. So if we similarly, you can just see that if we multiply n many elements together, then, and each of the shares are NT shares. So n many NT shares. Okay, I could not say n and n together. Okay, so if we can multiply m many shares, this NT shares, so that will give us n comma MT share. Now, the question is that without any kind of interaction, we have to, well, what was the question? Without any kind of interaction, we have to compute this, the determinant of any shared matrix can be computed correctly without any interaction. So that means that, oh, sorry, this MT, this has to be less than the resilience. What was that? Sharing, semi-secret sharing, T-sharing of the optimal resilience required for this. Okay, so we
M
cannot use
minus t. N is greater than.
no, but we have to find the optimal resilience for the semi-secret sharing. Optimal resilience means that the number of parties that who cannot generate the secret. So in this case, it says that if this is an I mean final after the final computation, if this is n times empty share, yes. So since this is a m by n matrix, right? Yeah. So m cross m matrix. So after the final computation, we have this empty many shares. So that means that this empty has to be m times t. It has to be greater than, sorry, not greater than. It has to be less than n. But the problem is that we cannot use any kind of interaction. We cannot use any kind of interaction means that Okay, sorry. Okay. Yeah, so we cannot use any kind of interaction, means that if we just do this multiplication individually, we can just multiply. So that will give us a n times empty share, and we can reconstruct the secret from this share only when this is true, right? So the resilience, this has to be less than m over m. But in the question, it is given as n over m minus n, m minus 1. Why? Determinant of the share of the matrix correctly. Determinant of any shared matrix. Any shared matrix. The matrix have m cross n. The dimension of the matrix is m cross n. So the determinant should have, each of the terms should have n many matrix elements. And if we can multiply n many elements together, so then that should give us n comma 40 actually wait. Okay, so what if we do this? We have n many elements, meaning that if there are 4 elements, let's say, we can multiply these two together, so that would give us 2t, and these two together, that would give us 4t. So yeah, that will still give us 4t. So t has to be less than or equal to. So mt has to be less than equal to, and then t has this equals to this.
N should be greater than MT.
M. N
N
should be
should be
greater than,
MT.
strictly greater than. Why? If it is equal, what is the problem? If mt is equals to n, then all n many part, oh no, sorry, that should not be true. If mt is equals to, so mt, so if this is true, so that means that mt plus one many element, I mean one many or mt plus one many people come together, sorry, parties can come together and they can generate the secret. So that should be the case. But in that case also we have this, sorry, t less than equals to this, not
And
the other way
T
around.
T are the parties which should not be able to reconstruct the
Yes,
secret.
yes,
So that's why they have subtracted from MT minus T.
mt minus t. No, no, no. When t is the resilience. I mean, I think I am doing some problem over here. Multiplication of n many matrix elements, right? So each of these terms are multiplication of n many terms, and we are adding them all up, and the addition doesn't take any extra communication. Okay. If we multiply n many elements together, so that should give us 2t. This should give us 3t. This should give us 4t, because we add them together, so the degree would be as added up. We multiply m many elements together, so that would give us n comma mt. So then mt plus one many elements, sorry, m many parties, they should be able to reconstruct the secret. The optimal resilience. Okay, so m plus one many parties should be able to reconstruct the secret, meaning that m plus one many parties should be able to reconstruct the secret, and we have to find the optimal value for t. N minus 1. It has to be greater than n minus 1. So n minus 2 over m t. Sorry, less than t. No, it doesn't actually. Okay, anyway, I mean, there is some problem that I'm facing over here, but this is true. I mean, if MT is the number of part, I mean, MT is the degree of the polynomial, then MT plus one many elements, they should be able to generate the secret, and therefore this should be less than equals to n, and t should be less than equals to n minus 1 over m. That should be the case. And it is also true that this is actually less than n over m minus 1. That is true. But why this is considered as the optimal resilience? So that I have to look into. Anyway,
And sir,
S2,
the
S3, and S4.
communication complexity will be m square times of bg. I think communication complexity I have issued at. Why they are saying that they are same of BGW?
Yeah, I think you should raise this question in the forums. And even if we have, so last time I told you that if we have any problems regarding this, assignment questions, so you should raise that in the Q&A forum.
Okay, sir.
So there is a Q&A forum, right? So you can raise questions over there.
Okay, sir.
I mean, if you have any confusion about the answer, if you have any doubts over there, so you can also raise there. I mean, even the instructor will be there to address your problem.
Okay, sir.
Okay.
Sir, there are some questions of in assignment 5 that I do not understand. Can you can you explain the questions to me?
Okay. Okay. Which question?
In assignment 5, there is question number 3rd.
Okay. Question 3, it says P1 to Pn and n is 2t plus 1 parties, out of which the adversary guards t many parties. Okay. In order to generate correlated randomness, the parties perform the following protocol to generate the protocol denoted as Gen Biva. Each party Pi performs NT secret sharing for A1, Pi, and Ci, and such that AI belongs to this, and Ci and Ci is equals to AI times Pi. Okay. NT sharing secret. Each party Pi performs NT secret sharing with 3 values. And Ci is equals to this. Then AI, Bi, Ci, these are generated. Okay. The parties then perform GRR degree reduction method to compute the following shares. The product of AI, Bi, and Ci. Which of the following options is correct? Okay. Okay, so in that question, what they're asking is something like this. So the protocol that they are defining is something like this. So first we have so this Gen Beaver protocol, what it says is that okay, NT semi-secret sharing AI, Bi, sharing of 3 values. Semi-secret sharing of 3 values. AI, Bi, Ci. Okay, so technically we have all these parties P1 to up to Pn, right? and each of them generate this AY values. Well, first of all, okay, AI, BI, and CI, where the CI is nothing but AI times BI. So in this case, this is not I, this is 1. Okay, and similarly, they generate P2 generates this A2, B2, and C2, where this C2 is nothing but multiplication of A2 and B2. And similarly, Pn generates An, Bn, and Cn. So this AI, BI, CI, these are not shares, these are rather random values, and these are generated. Okay,
No, but in
so
question,
these
I think they are also showing that in first point, each party will generate the share of these values.
yes, NT sum is secret sharings of these 3 values. So means that this AI is now we generate a sum is secret sharing for this AI, and all these shares, these are denoted by this A1. Means that
Yes.
this is nothing but the shares of this A1, A2 up to AN. So n many shares of this particular value A1.
Yes, sir. And
Okay,
in
so
step
that those are
two,
generated.
I think they are multiplying the shares of party one
Yeah.
with the shares of the party two.
Yes. So basically, once we generate this A11 and the share of A1, share of A2, share of A3, and so on, the share of AN. Okay. So these shares are nothing but, let's call it as A11, A12 up to A1N. Similarly, we have A21, A22, A2N, and AN1, AN2, and ANN. Okay, so these are the shares that are generated. Okay, and party 1 has this, party 2 has this, party 3, party 4 had this, and these are now shared among all the other parties, like party 1, party 2 up to party n. Okay, so now they want to figure out what is the share of this, the multiplication of all this. So the multiplication of all I is equals to 1 to n. So this is corresponding to that. They want to generate the shares of what are the shares of this particular value,
So they
right?
will multiply this A11, A12 up
Yeah,
to A1N, and
yeah,
then it will generate its share again.
yes. It will generate. Wait. Which of the following options is correct? Such that which party PI performs an anti-Shamish sharing of 3 values, such that this and here greater by this. Each party then perform the GR degree reduction method to compute the following sharings, A, B, and C like this. Okay, Gen Weaver generates. Okay. Yeah, so what was the question? Can you please state again?
So my question is that in second step, what they are doing in step number two, A means they are multiplying the shares of A and then secret sharing it.
Oh, no. I mean, if we want to, so they what they do want to do is that they want to generate the multiplication of these, I mean, multiplication of all this A1, AI to AN. Now they are considering this A value, sorry, this A is equals to the product of all this AI. So they do not know what this A value is. So they do not know that. They do not want to reconstruct that. They just want to find out what is the share of this particular A is. So that once those shares are generated, if they try to reconstruct those shares, then they should be getting back this A. So that's what they want to do.
Okay, so that shares get multiplied.
Yes, so now right now they do not multiply these shares over here. So in order to generate that shares corresponding to this, so let's say this is share A1, share A2 up to share AN. So after reconstruction, they should be getting this value. So this, in order to generate these shares, they use GRR protocol, meaning that for multiplying these two, they have one GRR protocol. And after that is generated, so that should be multiplied with the shares of this P3. So that is again one GRR protocol. So there will be total n many GRR protocol.
Okay.
Or not n many, n minus 1 many GRR protocols.
Hmm. Okay, sir.
So that's what it has been given in the question, that this is the way that this Chen-Weaver algorithm works. Now the options are given. You have to find out which one is correct.
Okay. And sir, next one question I have issue is this fifth question.
Yeah. And the fifth question, what was the question? Okay. So P1, let P1, P2, Pn in 2t plus 1 parties, out of which that was records t many parties. The parties holds nt sharing of 2 points A, B denoted by this, and wish to compute a random nt sharing of the product. Additional information about A, B is leaked to that person. No additional information. Okay. Assume that additionally that the parties hold nt shares of unknown uniformly random field R, denoted as R, and hold n2 sharing of the same element R denoted by this. And the parties perform the following protocol called the mult. Okay, just write it down first. So first we have Shamir secret NT Shamir secret sharing of AB. So corresponding to A, we have a NT secret sharing of A1, A2 up to AN, and also of B, we have an NT shares A1, A2 up to AN. And both of these are denoted by this. Okay, and the third we have also additionally the unknown uniformly random element R.
R is
They have
shared by T and 2T polynomial.
NT. Yeah, so first of all, this NT is like this, R1 up to Rn, and this is denoted by this, and it also have a N to T shares. We can call it as R dash 1, R dash 2, R dash N, and this is denoted by this angular bracket. Now the mult operation says that locally they compute N to T shares of the value VAB plus R. So what they can do is that they can locally multiply this. Okay, sorry, this is B1, B2 up to Bn. So they locally multiply this A1 and B1, okay, in the first case, and then it will add it to this R1 dash. So if they do that, so that should be this. So V is basically is equals to A1 times B, sorry, VI is basically AI times BI plus this R dash I. So since so after multiplying AI BI, so that will basically be giving us a N2T share, right? So this will be an N2T share, and this RI, this is already an N2T share. So after adding, so this will be an N2T share. So VI, this will be an N2T share. N2T share of what? Of this value, AB plus R. Okay.
Okay,
So
sir.
this VI is basically the share of this value. So that is the first step, and after that, which is the second step, says that the parties send their entity shares to V, to party P1. The parties send their entity shares to V. Sorry, shares of V to party P1. So all these shares are now sent to P1. So P1 takes all the shares VI. So VIs are sent to P, and P. So P1 now reconstruct V and reconstructs the secret share V using the shares, and it receives in step 2 and on share. Now P1 sends this V to all the parties. So P1 can now reconstruct V. So that information does not really leak to anyone. This information about AB, because as you can see that this R is not known to anyone. Okay, so AB will be known to, so AB will not, the information about AB will not be leaked to P1. So P1 generates V and sends it back to everyone. So that is step 2. No, that is step 4. And then all parties now locally computes the NT shares as this. Okay. Now, if this is known to everyone, this V is known to everyone. So every party knows what is this value V is, which is AB type plus R. Now, everyone has this, the shares of R, the NT shares of R. Now, if they compute this V minus RI as their, let's say, XI, V minus Ri, so this will be nothing but the share for V minus R. So this X is nothing but V minus R. So the V minus R should be the actual value of AB. And in order to generate the V minus, the shares of V minus R, they just compute this V minus Ri. Xi is equals to V minus Ri. So at the end of the day, if they try to reconstruct the value of X from all this x1, x2 up to xn, so they should be getting back this V minus R, which is nothing but AB.
I think
So
this
that is the
protocol
protocol.
is given by DemGuard. I think this
Yeah,
protocol is
I
given
think,
by someone
yeah,
to do efficiently compute AB without degree reduction.
yeah,
Okay, sir. Okay, I will try these questions.
okay. Oh, sorry. Okay. Okay, and the next two questions I've already discussed, this GRR degree reduction method. I have already discussed that in the initial, I mean, in the this beginning of the of this session, and also this was already discussed in the lectures. Why there does not exist any two-party protocol. So
Yes, sir.
I mean, it was discussed in the very detailed manner, so I don't have to discuss it over here. Okay, so okay, so this is the end of today's session. We will meet again next week.
Thank you, sir.
And yeah, thank you.